All right. So we're going to start the circular motion unit here today, and we're going to talk just about kind of the basics. Okay. So we'll be looking at what we call uniform circular motion, which is when an object moves around and around in a circle at a constant speed. Okay. There's going to be some stuff that's going to seem contradictory, but we'll explain it. And there's going to be a little bit of stuff. We might get to the stuff where Newton's second law actually applies to this as well. I don't know if we'll get to that today, but we will eventually get to that. So we're going to look at what circular motion is. It's when something goes around and around in a circle. See, this unit's getting easier already. We're going to understand how circular motion happens. Okay, for something to move in a circle, certain conditions have to be present. And we're going to look at the relationship between period and centripetal velocity. So period is a new term for us in terms of physics. Okay, what period means is it's the time for one cycle. Okay, so time for one cycle, that's the general physics meaning of it. So for circular motion, it's the time it takes for one circle. Okay, in simple harmonic motion in waves, which is our next unit, it would be time for one oscillation, so one complete movement of the wave or something like that. Okay, so period is the time for one cycle. Typically, we measure that in seconds. Okay, we also sometimes use frequency, which is the inverse of period. Okay, so frequency is how many cycles per second. Okay, whereas period is seconds per cycle. Okay, so one is cycles per second, the other is seconds per cycle. So they are the inverse of each other. Okay, which is where our first formula comes from. Period, which is capital T, is 1 over frequency. Okay, because they are the reciprocal of each other. Okay, going 1 over each other allows you to go from seconds per cycle to cycles per second and vice versa. Okay, period and frequency are often used in our next unit as well, okay, especially when it comes to sound. Okay, frequency of sound is what we associate with pitch, okay, but it's going to be quite important when we're talking about circles and stuff too. Okay. Everyone get the cartoon? As if they would have that button on your seat. I know it's Monday, but come on, that's kind of funny. All right, so if something is undergoing uniform circular motion, okay, it's traveling at a constant or uniform speed. It is not, however, traveling at a uniform or constant velocity. Okay, now up until this point, when one was true, the other was true basically all the time. Uniform speed and uniform velocity kind of meant the same thing. But in this case, it is possible for something to have a constant speed but be accelerating. Because the definition of acceleration is a change in velocity, not a change in speed. Okay, now velocity is vector. So if we're changing direction, we're changing velocity. And that requires a force to produce that acceleration. Okay, that's kind of what we learned in Unit 2. Okay, if an object is going to accelerate, that is change its velocity, whether that's magnitude, direction, or both, okay, is going to require a force to be present. So if I'm whirling something around and around in a circle like this person is, they've got a little toy plane on a rope, okay, they're swinging it around and around, the magnitude of the velocity vector is constant. Okay, this arrow is the same length all the way around, but the arrow doesn't point the same direction all the way around the circle. So the direction of the velocity is always changing. Okay, everyone kind of follow me there. So to move in a circle, okay, an object has to be constantly accelerating, even though its speed is not changing. Okay. All right, everyone kind of follow me there. Now it seems weird, but it's constant speed, but it's accelerating. Okay, but the velocity is changing, just the vector of the velocity is changing. Now, which way is this object? If it's going to go in a circle, which way is it accelerating? Because the direction of the acceleration is always the same. Actually, not away, towards. I mean, think about it. If you're whirling something around and around in a circle, which way are you pulling it? Towards the middle, right? Like if you have a weight on the end of a rope and you're whirling it around and around in a circle, you're pulling it towards you, and you're the center. Okay, so in order to make something go around and around in a circle, you have to pull it toward the middle. Okay, everyone kind of follow me there? Okay, there's this idea that that there's this force that's trying to pull it away. There actually isn't a force trying to pull it out of the circle. It wants to go out of the circle because of inertia. Inertia wants to go in a straight line. You are preventing that by pulling it back towards the middle. Okay. Okay, so sometimes it's more convenient to describe uniform circular motion by specifying the period of the motion. That is, how long does it take for the object to go around the circle one time? Okay, so we can calculate the velocity of the object as it goes around and around the circle. Okay, or sorry, the speed of the object as it goes around and around the circle, as long as we know the distance and the time, right? I mean, this is the oldest formula we've been dealing with, v equals d over t. Agreed? We can't calculate velocity because if we used v equals d over t, the displacement would always be zero because it would always be coming back to the same point in the circle. Okay, so we're actually calculating the centripetal speed here, okay, by calculating the distance. Now, what do we call the distance around a circle? Circumference. Okay, and we can calculate circumference either by going pi times the diameter or 2 times pi times the radius. Okay. Everybody all right with that? Those are the two ways to calculate circumference. Okay, so all we do then is substitute this in for d and substitute period, the time it takes for one cycle, in for t, and we end up with our first formula. Okay, well, sorry, second formula, because we talked about t equals 1 over f, right? This is our kind of fundamental calculate the speed formula, okay, for this unit. V equals 2 pi r, so the circumference, divided by the period. Right? So the circumference of the circle divided by how long it takes to go around the circle one time. When you are doing this calculation, should you use 3.14 or should you use the pi button? Use the pi button. Pi basically never ends. Okay, it's a ratio, but it basically is a number that never ends. So you do need to use the pi button on your calculator, as that will be a great deal more accurate, especially when we start dealing with like celestial distances. Okay, not having all those other decimals when you're multiplying by the radius of Neptune's orbit can kind of make a big difference. Okay, so make sure you're using always the pi button when you're using doing your calculations for this. You can, but we so rarely ever get the diameter of anything. Most of the time you're given the radius. Yeah, so we just use that one more often. Okay, any other questions there so far? All right, so very common kind of application of this is in balancing tires on a car. Okay, if your tires are not properly balanced, you're going to notice it. And it's going to be like at certain speeds, your car will like basically start to shake. But then once you get past that speed, it'll kind of smooth out, right? And then you'll notice that there's kind of certain speeds where that happens. I once had like some snow got inside and kind of froze on the inside of my rim. So I added all this extra mass to one side of my wheel. And when I got up to about 40 clicks an hour, my car would start to shake. If I got up to 60, it was fine. And then once I got a little faster and I got up close to 80 again, it would start shaking again. It was kind of this, there were certain speeds where that weight really started making the tire wobble, right? Now, the process of making tires is not perfect. They essentially pour liquid rubber into a mold, cool it, and then pull the mold off, and there's the tire. So it doesn't always get exactly the same amount of rubber on all parts of the tire. So when they install a tire on the rim, they usually put little weights at various places on the wheel in order to make sure that your tire is thus balanced, because you don't want to have your car shaking. It's bad for control of the vehicle, safety first off, okay? And secondly, it's really hard on the suspension and things like that because the car is always shaking. It's hard on it. So what they want to do is always make sure that your wheels and tires are balanced so you never have that problem. So what they do is they put the wheel with the tire on it on this machine that's just going to spin it around and around. But the machine is essentially on a spring. So it can start to detect when the wheel starts to shake. And when the wheel starts to shake, it can detect which side of the wheel is lighter. And then what they'll do is they'll put little weights on. Sometimes you can see them. Okay, on older wheels, they kind of stuck out and they kind of went like this over the lip. Now they're actually little square sticky weights that they put on the inside of the rim. Okay, they're a little less noticeable and they're less likely to fall off. Okay, how many people have ever seen those on their wheels? Okay, next time you look at your wheel, look at it. You'll see them on there. Okay, it's just there to keep the car, give you better control and actually balance the tire. Okay, so we're going to do this example problem to do with this machine here. So it's balancing a wheel that has a radius of 0.29 meters and is being rotated at 830 revolutions per minute. Okay, did they give me a frequency or a period there? They gave me a frequency. They told me how many times per minute this thing revolves. If they had given me the period, they would have told me how many minutes it takes for it to revolve one time, which is still going to be a really small number. Okay. All right. I probably don't want it in revolutions per minute. Okay. I probably want it in revolutions per second. Yeah. All right. So I'm just going to convert that. Is it going to travel around more times in a minute or more times in a second? Less times in a second. Yeah. So do I want to multiply that by 60 or divide by 60? I want to divide by 60. All right. So this thing goes 830 revolutions per minute, which means, whoop, not 83, 830. Which means it only revolves 13.83 times per second only. That's still pretty fast. Okay, it goes completely around in a circle 13.83 times in 1 second. Okay, we can call that RPS, rotations per second, or we often call it Hertz, cycles per second is what Hertz stands for, and that's what we use most often. All right, we also know the radius. Okay, the radius is 0.29 meters. Okay, and that's it. Now they're asking us to calculate the speed. Now the formula we got says that speed equals 2 pi r over t. I don't have t, I have f. Okay, but I know that t and f are related, okay, because we wrote down this formula on the very first slide. T equals 1 over f. Okay, so I have how many times it goes around the circle in a second. I want to know how many seconds it takes to go around the circle once. Okay, so I'm going to go 1 over this number to get the period so I can use it in this formula. Everybody all right with that? Okay, so it takes 0.072 seconds for this thing to rotate around in the circle one time, which is pretty fast. All right, so now that I have that number, I can use this formula here. Okay, so I'm going to plug in my numbers. 2 times pi times 0.29 meters, that was the radius they gave me, okay, divided by the period, which we just calculated as 0.072. We'll use all the decimals still that we got there. Okay, so we have 2 times pi, okay, and pi is right here, times 0.29 divided by 0.07. Okay, so the tire is rotating at 25 meters per second. Okay, so that's spinning pretty fast. You certainly wouldn't want to like put your finger over there or anything. Okay, get caught in the machine. Okay, so it's, whoop, sorry, I should have multiplied by 3.6. So 25 times 3.6 gives us, so it's moving at 90 clicks an hour. Okay, so the tire is spinning at 90 kilometers an hour. Okay, so we got 25 meters per second. Okay, everyone all right with what I did there? Could I have altered this formula so I didn't have to do this? Okay, if t is 1 over f, okay, then f is 1 over t, right, if I manipulate that formula. So could I just, if I know that this is 2 pi r over t, is that the same as saying 2 pi r times 1 over t? And 1 over t is f. So I could have just as easily said that, okay, and save myself a step. Okay, only one of those ends up on your formula sheet, and you're kind of expected to be able to figure that manipulation out on your own. Okay? And if not, well, then you just do the extra calculations, no big deal. Okay, so that's what we just did there. All right, so the definition of uniform circular motion emphasizes this. The magnitude of the velocity vector does not change. Okay, it's constant. But the direction is always changing. Okay? Because it's always changing, the object is accelerating, and we call that acceleration centripetal acceleration. Centripetal means center seeking, right? Because it's towards the center. Now, how many people, when I say centripetal, are like, that sounds like a word I've heard before, but not quite? Okay, how many people have heard the word centrifugal or centrifugal? Okay, so centripetal and centrifugal are not the same thing. One is a real thing and the other is imaginary. Okay, I say imaginary kind of tongue in cheek, but here's why I say it. Okay, centripetal means center seeking. That's a real force. Centrifugal means center fleeing. Okay, wanting to like go out of the center, so directly away. There is no force acting directly out of a circle. There is no such thing as centrifugal force. All right. The reason we feel like we want to leave a circle is because of inertia. That's centrifugal force. Okay, there isn't really a centrifugal force. There's just inertia. Okay, there's just this idea that I want to go in a straight line because of inertia, and something has to actually pull or push me back towards the center for me to do that. Right? Like when it's icy. Okay, if I try and take a corner when it's icy, okay, there's actually a tendency for me to like start turning and then just go straight. Okay, and I go straight because there's not enough friction to keep me in the circle. So I follow my inertia and go straight. Okay, if you're in a car with your friend who's kind of a crazy driver and they take corners at a high rate of speed, okay, you ever notice that you kind of get like thrown into the window? Right? Like if they make a left-hand turn, you're like, and you're into the window and you're grabbing the holy crap bar and hanging on for dear life. I don't know what that thing's really called. I just call it the holy crap bar. You all know what I'm talking about, that handle on the pillar. Okay. You know, you're hanging on to that. Well, that's because, okay, now it's the car's door that saves your life, or the window, or whatever, okay? Because your inertia wants you to go in a straight line, okay? But the door, thankfully, pushes you back towards the center of the circle, okay? It's not that you're trying to leave the circle, okay? So if this is the corner, okay, and you're going around the corner, okay, you want to do this, but the window pushes you this way. Regardless of what point in the circle you are, okay, the window always pushes you back towards the middle, okay, even though you want to do this. You want to go in a straight line. What you don't want to do, and there's no tendency or no force trying to do this, is this. There's no force trying to make you go straight out of the circle. It feels that way, but it's not that way. Okay, that makes some sense to people? Okay, the same is true when you're whirling something around and around in a circle. Okay, so if I've got this thing and it's just whirling around in a circle, were I to let it go, how would it fly? Exactly, in a straight line, tangent from wherever I let it go. Okay, so if I let it go when it's aimed at Michael, okay, like it's like if the tape is here and I let it go, it's aimed at Michael. Is it going to hit him? No, at this point in the circle, its velocity is that way. It would go towards the wall. Okay, if I wanted to hit Michael, I'd have to let it go over here. Okay, that way it's tangent to the circle that way. Okay, this is how David slew Goliath. Okay, he had to sling. Okay, and the sling is really just a leather strap. Okay, or in that time it probably would have been made out of hemp. Okay, and so they would have made this like pouch on the end of it. You put the rock in there, and then you fold the strap over so it's folded like this, and the rock hangs in here. Okay, and you whirl it around and around, which means you can get it moving way faster than you could by actually just throwing it. Okay, the sling gives you that speed advantage. And then what you do is just when at the point where you want to have it go at that speed, you just release one side. Okay, the tension is gone from the strap. There's nothing holding the rock in the circle anymore, and it flies out in a straight line from that point. Right? It would require a lot of practice in order to be able to pull it off. Okay, but that's how a sling works. Okay, it just uses the principle of this. Okay, I can get this thing moving a lot faster, okay, by whirling it around and around than I could ever possibly throw it. Okay, it's about length of the lever, right? By putting this extra distance, I've essentially made my arm that much longer. Okay, by making my arm that much longer, I can make it go that much faster. Okay, everyone okay with that idea? Yeah. Okay. All right, so centripetal acceleration is what keeps you, well, part of what keeps you going in a circle. You have to be accelerating towards the center of the circle. Otherwise, you're not going to move in a circle. You're going to move in a straight line. Okay, so the magnitude of the centripetal acceleration depends on two things. Okay, how fast you're going and the radius of the circle. Okay, those are the two things that can affect the centripetal acceleration. So the faster I go, the more centripetal acceleration I'll have according to this formula. In fact, not just more, but how much more? Exponentially more. V is squared here. If I go 2 times faster, I'll have 4 times the centripetal acceleration. 3 times faster, I'll have 9 times the centripetal acceleration. So the faster I go, okay, the more centripetal acceleration I'm going to experience. Okay, but the reverse is true for radius. Okay, so the further away I get, okay, the less centripetal acceleration I'm going to feel. Okay, everyone with me there? All right, so if I get, like, let's say I'm 1 meter from the center, I'm going to experience a certain amount of centripetal acceleration. If I'm 2 meters from the center, I'm going to experience less. Okay, provided speed stays the same, which it does. Okay, if I'm on this circle, let's say this is like the merry-go-round of all the stuff we watched. Okay, it doesn't matter where I am on this circle. Okay, it takes me the same amount of time to go around. Everybody follow me on that? Okay, but the further away I get, the farther I'm traveling in that same amount of time. Okay, so when we say that V is 2 pi r over t, we're saying that radius gets bigger, speed gets bigger. Okay, but if speed stays the same and radius gets bigger, I actually feel less acceleration. This is why I would want to take like a corner wider. Okay? If I take a corner narrow at, like, let's say 50 kilometers an hour, I take a corner really sharply, I'm going to feel a lot of acceleration. But if I take that same corner at 50, but I take it wider, I feel less acceleration. Everybody follow? Okay, so it's weird in that acceleration has a different relationship with radius than speed does. Okay, that's why when we're saying, like, those guys all wanted to stay near the center, that had nothing to do with acceleration, everything to do with how fast they were going to be going. Okay, once they got out of the center, they were going a lot faster. Okay, had the speed in the center and at the edge of the merry-go-round been the same, it would have been better to be on the outside of the merry-go-round. Okay, but that's not the way it works. Right? This is more about cornering. If I take a corner wider, I experience less acceleration and I'm less likely to lose traction. Okay, because I'm going the same speed I would have if I was going in the middle. Okay, right. So centripetal acceleration is a vector quantity. Centripetal acceleration, because it's centripetal, is always towards the center. Okay, centripetal means center seeking. So in this unit, we'll use vectors a lot less, unless a question specifically asks what direction is the centripetal acceleration. You don't need to write it because centripetal means towards the center. Okay, so we'll use the vectors a lot less here because centripetal by definition means into the middle. Okay, same is true for the moon orbiting the Earth. Okay, the force of gravity keeps the moon in orbit around the Earth. Right, so the moon is always accelerating towards the center of the Earth, but it never gets any closer because it's going so fast. In fact, it's going fast enough that it's getting a little bit further away all the time. Okay, so the moon's orbit is actually not a perfect circle. It's a slightly expanding spiral. Don't worry, the moon's not going to go away anytime in your lifetime. Okay, it's going to be around for a long time, but it is getting steadily further away by about 2 centimeters a year. It's not much. Yes, Yeah, and because because the moon's orbit isn't, it shifts, and not because like it's just weird. It's because of where the nature of the Earth and the sun are. The Earth and the moon actually wobble back and forth a little bit due to each other. So sometimes the moon is closer to the Earth than it is in other times. So sometimes we get extremely high tides, and sometimes we get our high tides that aren't very big, and so on, based on where the moon is. Okay. So this is what we talked about here with the David and Goliath thing. So we've already seen the video there. Okay, clearly shows that an object in uniform circular motion would fly off in a tangent if it was suddenly released from the circular path at any point. Okay, so the object would then, according to Newton's first law, move in a straight line at a constant speed, okay, to another point. All right, so if we were talking about here's the circle, okay, here's point O, right? It would fly off in a straight line to this point. And if we were trying to hit something with a sling, we would have to know where that point was. No. You mean like if you like was whirling and walked up and smacked them with it? It would probably deliver about the same impact. Yeah, it would be moving at the same speed either way, right? I mean, in the perfect physical world, it would actually deliver more if you could walk up and smack him with it, because air resistance is going to slow it down along its path. Yes. Yeah, a ball and chain mace would work along the same principles, in that you can swing that weight faster at the end of a chain than you could just if you had it on the end of a stick, right? I mean, still, even having on the end of a stick gives you more speed than if you held it in your hand. Right? But yeah, on the end of a stick with a chain on it, yes, you spin it a lot faster. Plus, it gives you extra reach, right? Your opponent can't hit you, but your weapon is longer, right? But of course, you do have the one problem with anything getting longer, being that its time of rotation is greater, so you leave yourself open to attack while it's rotating away. Okay, so this is what I was talking about a minute ago. In terms of speed, radius increases speed. Okay, if I'm going around, if I'm going around on a merry-go-round, if I go to the outside, the period is the same. The radius gets bigger, I go faster. But in terms of acceleration, it's inverse. So if I take this small corner that only has a radius of 320 meters at 28 meters per second, the occupants of my vehicle are going to be thrown into the windows, grabbing the holy crap bar, hanging on for dear life, okay, whatever. If I take this same much wider corner, in fact 3 times wider, at the same speed, okay, so I haven't increased my speed, I take it at the same speed, my passengers will feel a lot more comfortable in the car because there'll be less centripetal acceleration. Okay, everybody all right with that? All right, so let's say we want to figure out what the centripetal acceleration is for both of these cars. Okay, so we know the formula, because we got it just a minute ago, is v squared over r. Okay, so the centripetal acceleration for the first corner, okay, is going to be 28 squared divided by 320. All right, so the acceleration experience there is 2.45 meters per second squared. Okay, so I mean, that's considerable. That's about a quarter of a G. Okay, so you would feel like you would feel a little heavier in that direction, about a quarter of your mass. So if you weighed 100 pounds, you'd feel like you were 125 going that way. Okay. In this corner, that's 3 times bigger, how's this number going to look? It's a third as much, right? Okay, it's going to be 3 times smaller because the corner is 3 times bigger, right? But we'll double check it. So AC on this one's going to be 28 squared, because we're keeping the speed the same, okay, divided by now 960. Okay, so 0.816. So if I multiply that by 3, right, I get 2.45. So yeah, my passengers will feel a lot more comfortable in this situation. Okay. Yes, they'll feel a little bit pulled to one side, but no more than you do anytime you turn a corner. Okay. You guys are fortunate. Your cars are much safer now than when I was in high school. I had a buddy who had a Jeep YJ back in high school, no doors. You could take the doors off. Yeah. You can with the new ones? It's crazy. It's crazy that they even allow that. Okay. If you, yeah, weren't wearing your seatbelt, he could throw you out without touching you. Okay. All he had to do was take a corner really fast and out the door you'd go. Okay. Not that we ever did that, because I was never young and stupid. Right. Yeah, never. Never in that. It was usually just on the river bank in the mud. Yeah. Nobody ever got hurt, luckily. And that's all it was. It was just luck. It wasn't, yeah. Okay. So this is the calculation that we just did. Okay, we found that yes, the acceleration on the shorter corner is 3 times greater because it had 3 times less radius. Okay, on that one. All right. Now the effective speed. Okay, we didn't look at. Okay, so what if I took this same corner? Okay, let's say I take the 320 meter corner, but now instead of taking it at 28 meters per second, I slow down and I take it at 14 meters per second. Right? So originally it was 2.45 meters per second squared. If I reduce my speed by 1/2, how much less acceleration will there be? Won't be the square root of 2.45, but you're close. I'm cutting my speed in half, and it's exponentially related. 1/2 squared is 1/4. Okay, so the acceleration experience here should be 1/4 if I cut my speed in half to 14 meters per second. Whoop. Okay, so I reduced the acceleration by a factor of it's down to 1/4 of its original value. Okay, by reducing my speed by a factor of 1/2. Everyone kind of follow me there? I mean, it's common sense, right? If it's, see a big corner coming up, our natural reaction is to slow down, speed up, slow down a little bit, okay, before we get there. Because we know if we go too fast around a corner, we'll lose it in the corner, okay? Okay, so I want you guys to just give me some quick answers here just on paper, okay, to question 2, for sure, all 3 parts of question 2. Okay, and question 5. So let's go 2, 5, and 6. Okay, I want you to write down some answers to those that we can talk about here in a few minutes. So if you make a turn, and this would be on a corner that's flat, not a banked corner, okay, but a corner that's flat, what's keeping you in that corner? Friction. Yeah, the force of friction between your tires and the road is what keeps you in that corner. If the corner is banked, like interchange, okay, like out here when you get onto Highway 2, okay, that's banked. That allows you to use both friction as well as a bit of the normal force of the road. Okay, because as you go around the corner, you push into the road. Okay, the road pushes back, and there's a component of that that's directed towards the center of the circle. Okay, in fact, most of them are designed. We'll talk a little bit more about this tomorrow, or sorry, not tomorrow, but Wednesday. Okay, most of them are designed so that in adverse weather conditions, if you take them at the recommended speed, you don't need any friction to stay in the corner. Okay, in fact, I once saw on the old Highway 22 from McLeod interchange there, where you coming from eastbound 22X onto McLeod, I actually watched a person slide in to the middle. Okay? It was so icy, and they went too slow. Okay? Like as a physics guy, I was watching behind, going, "Oh crap! If you don't, I'm going to have to pass you on the exit ramp on the ice because you're going so slow. You're going to," and then slid right into the middle. Okay. Yeah, okay, just could see it coming. Okay, they started sliding. I could see it coming because I could feel my car actually starting to do the same thing because I was stuck behind them. Right, they slid into the middle and I sped up. and didn't slide into the middle. Okay, so they're actually built so that even under the worst possible road conditions, if you take them at the recommended speed, you are safe. You won't slide out of the corner, but you also won't slide into the corner. Okay, but you go too much one way or the other, and you're going out or in. Okay. All right, B, a ball tied to the end of a rope and spun in a circle. Tension, yeah, the tension in the rope is what's keeping it in the circle there. Okay, and the moon moving in a circular orbit around the Earth is gravity, yeah. Okay, lots of things can act as a centripetal force. All right, gravity is probably the most common one. Okay, friction is also very common. Okay, and if you're just whirling something, then there would be tension or some other holding force. All right, question number 5. If I'm pedaling a bike at a constant rate, describe the motion of the bicycle if the wheels were not circular, but oval. So in an oval, the radius of the circle, well, because it's not a circle, is changing. It's not constant. All right. So what happens to your speed? Is your speed constant if your wheels are oval? No, you're going to speed up and slow down, speed up and slow down, speed up and slow down because your wheels aren't round. Okay. So there would be this really uneven kind of make you seasick sensation. Oh, then it'd be horrible. And that would happen almost immediately because you're always going to have slippage from the powered wheel. So yeah, you would never be able to keep them in sync with each other. Yes, and in fact, magnetism is used a lot of the time for, like, especially back in the day when we had like the old style TVs, the cathode ray tubes, okay, so not the flat screen stuff, that actually used a magnetic field to direct electrons into certain parts of the screen, right? So it would alter their path by increasing or decreasing the force on them, okay, to make them hit different parts of the screen. So yeah, magnetism can also be a centripetal force. And in fact, if you take physics 30, there's quite a bit of stuff in the electricity and magnetism unit where forces and fields come in. All right, for number 6, the relative speed of a pebble stuck in the tread of a bicycle tire and the ground. Explain why the pebble is not dislodged when it comes into contact with the ground. Suggest a method to dislodge the pebble while still riding the bike. Okay, you get a rock stuck in the tread. What's holding it in there? Yeah, well, it's mostly friction, right? How many people have ever had a rock hit them in the windshield? When does it usually happen? Okay, well, yes, when you're traveling, I should have been more specific. When you're traveling behind someone, yes. What is the person in front of you doing? Speeding up, slowing down, or traveling at a constant speed? Yep. Most of the time, the rocks come out when they're accelerating. There's enough friction to hold them in up to a certain speed. Okay, and then when the wheel gets to that speed or beyond that speed, the friction holding the rock in the tread is not sufficient to keep it there and it flies out, right? So always be aware you're most likely to get a rock in the windshield when the car in front of you is changing its speed, and that is going faster, not slower. Okay, so if it's speeding up, that's when the rocks are likely to be dislodged. So how can you dislodge the pebble while still riding the bike? I actually had a person go, get a stick. Like, yeah, that's going to end well. No, just ride faster. Okay? If you ride a little bit faster, you might get beyond the ability of friction to hold the rock in the tread, and it'll fly out. Yeah. And it's the same reason why when you were a kid and you drove your bike through a puddle, what happens to your back? Yeah, you get the big streak of mud right up your back. I know my kids come in that way all the time, and I'm just like, are you kidding me? Anyway, yeah, it's the same idea, right? It just picks, the water gets into the treads of the tire and it stays there until it gets going fast enough and it sprays a little higher. Okay, be ready for your test tomorrow. There's no quiz, by the way, in case anyone was thinking there might be. Yeah.